4-leaf rules, you have something like this. Let me just copy from the book. R equal to cosine of 2 theta. And if you graph this, let me just copy from the book, okay? You're going to see something like this. Okay. Of course, the book draw better. This is the equation. The graph of the equation of R equal to cosine 2 theta. So using polar coordinate, you can actually draw more other things. Of course, more to go. I'll just try to demonstrate some of those. Okay, now, if you have a curve and you want to find, let's say, the tangent line at a point on the curve, and we're going to apply what we learned before for parametric equation before. You know that x equal to r cosine theta, right? I just showed you that. Y is equal to r sine theta, right? The slope of the tangent line, slope of tangent line is always what? dy over dx, right? So you're going to calculate here dy over d theta, dx over d theta. This is what? dy over d theta. We used dt before for the parametric, but in this particular it's going to be theta for the variable. And dx over d theta. My theta is too big, so d theta. Okay. So you a little bit of calculation in here. If x is equal to r cosine theta, keep in mind that r is not a constant, okay? R is a function of theta. So dx over d theta equals to, now we have to use the product rules in here, right? Of r times cosine theta, so dr over d theta times cosine theta plus r times derivative of cosine is negative, so negative sine theta. Okay? Y is r sine theta, so dy over d theta. Okay, so dr over d theta times sine theta plus r times derivative of sine is cosine of theta. I'm using product rules in here. Derivative first times the second plus derivative second times the first. I have this. Okay, so dy over d theta is this, and dx over d theta is that. You plug it in, you have, put it in here for you. dr over d theta times sine theta plus r cosine theta over dr over d theta cosine theta minus r sine theta. And then they give you the actual value, what is theta equal to, what is r. Okay, you got r, you got theta, you plug it in, you have dy over dx, which is the slope of the tangent line, and you have a point, you find a point, you have the tangent line. So it's a little bit more complicated, right? You do more work. It's still doable. Okay. Let's do some more calculus using the polar coordinate. One application of polar coordinate is this. Say r equal to a function of theta, right? R function of theta. You have this. So you have a curve right here. R theta. And the book write this way. R equal to f of theta. R as a function of theta. And like x equals to f of t, right? So usually I write r is a function of theta. It's the same. Okay. And say you want to calculate the area bounded by the two lines from angle alpha to angle beta. Okay, this is the region that we want to calculate the area. Be careful, okay? This is what changing is the angle we're changing, and this is the curve that we're talking about. It's not like bounded by the x-axis and two vertical lines. We're talking about a section, like a slice of pizza. Okay, and same ideas in general, in calculus in general. You want to calculate the big area, you chop it down to very small slice of pizza right there, and then you calculate the area of one piece at a time. And we use the formula of area of a circle is pi r squared, right? Okay, and for the whole circle. So for one slide is the angle is not pi. The angle is, if the angle is theta, then what? Theta over 2 r squared. the angle is just a little bit, so d theta, and then used to be able to write this way, 1/2 r squared d theta. If the angle of theta is theta over 2. The whole circle right here is 2 pi, then the area is pi r squared. So half of the angle, right? So the angle of theta is going to be theta over 2 r squared. The angle is a little bit of changing because d theta over 2. And used to be able to write d theta at the end. We have the formula. Okay? So area for that slide is going to be 1/2 as a constant. I put it outside, and then r squared d theta. Okay? So I'm not going to calculate the integral, but I can show you an example. Say r equal to cosine of 2 theta. Then the say this is the curve of r equal to cosine of 2 theta. Not right, but show it that way. And theta from 0 to pi over 4, for example. Then the area bounded by this region right here is going to be 1/2 integral from 0 to pi over 4. R squared is going to be cosine square of 2 theta and d theta. You have to integrate it. You have the area. Okay? You use a half angle formula in there. And then a little bit more general. Say if you have 2 curves. This is my first curve, and this is my second curve. All right? This is, say, R1 equal to F theta. And the second curve right here is R2 equal to G theta. And you want to calculate the area bounded by the 2 function R1 and R2 and the angle from alpha to beta. Very similar to calc 1, right? If you do integral of R1 squared d theta, you have this area, the big one. Okay? And if you do integral of R2 square theta, you have this area right here. The green one. So all I have to do is do a subtraction. I have a difference. So in short, people are going to write this way, integral from alpha to beta. This is the angle, alpha to beta. Okay, of R1 squared, which is F squared theta. Let's subtract G squared theta. Okay, d theta. And that was the idea. Okay. Alpha and beta is the changing of the angle theta, say from 0 to pi over 4 or something like that. Okay. And then the last one before I stop, so all I'm showing you is what whenever you have polar coordinate, you can always convert it back to x, y, and vice versa. Okay. Not sometimes, I mean, say it this way. Whenever you are dealing with an object involving angle or rotating, then you should think of polar coordinates. Whenever you deal with something with square, okay, with up and down, then x, y coordinate. And then we have the Euclidean formula. Before, what was Euclidean L? Integral from a to b, right? And that's square root of, what was that? dx over dt square plus dy over dt square dt. Right. Okay? And now dt is changed to d theta, because t is just a dummy variable. And I showed you dx over d theta already, dy over d theta already. You plug it in, you have, what was dx over d theta? Dx over d theta was, let me look it up, I just wrote it. What's what? dr over d theta times cosine theta minus r sine theta. Okay? And then dy over d theta is equal to dr over d theta times sine theta plus r cosine theta. And it looks ugly, but actually when you square this one up, and then you square this up, right here, you add them up, simplify. It looks very simple. Okay? I'll let you multiply them all out, combine like term by yourself, but you simplify. This thing is really this. Square root of r squared plus dr over d theta squared d theta. Right? So it's really short. R squared and then the derivative square. The math comes from here. Okay? And that is how you have the formula for the area and the arc length. Usually, the exercise in this section is not too hard because it's like introduction to the polar coordinate. So I'll do it on purpose, just show you the formula, and I'll let you to work on the problem on your own. And I strongly encourage you to ask questions if you got stuck anywhere, okay? And just ask and I'll show you more. And out of Calculus 2 course, this chapter 10 is, in my opinion, this is the nicest one, the easiest one, because your math is not going to be so hard. You try your exercise and you see it, and that's usual. Always more than welcome to ask questions. I'm very happy to answer yours, okay? Just ask. And let me stop the session right here. Thank you so much for watching, and have a good week, everyone. Bye-bye.